So yesterday we went over a few more examples of Newton's second law problems, okay, or applications of Newton's second law. So we're going to look at today, okay, are even more, but we're going to get more complex. Okay, and it's not that the math gets any harder. The math doesn't get any harder. Okay, you've already seen what the math is. It's vector sum of all forces and F equals m times a. That won't ever change. What changes is being able to see how the forces work in that particular problem. Okay, and hopefully by the end of the unit, you will see the world as I do. It's a dark and scary. No, it's okay. But you'll see it. Like when I look at stuff, I always see, oh, okay, so that's what's going on there. That's what's going on there. It annoys the heck out of my wife because I'm always, well, see over there, like that's pulling that thing in that direction. And she's like, do I look like I care? No, but you should.
What does she do?
Okay? She used to write contracts for oil and gas companies.
Oh, yeah, she
Yeah.
really wouldn't care.
No, she wouldn't. No. Okay, so I want you guys to see if you can figure this one out. Okay, it sets up like this. These two boxes are connected by a rope, okay? And then there's a rope connected to the first box that's being pulled, all right? So the force pulling in here, so by the hand, is 55 newtons. The force of friction, okay, on the block system is 44.1 newtons. Calculate the acceleration of the blocks. Okay, I'm going to give you a couple minutes. Mathematically, this is one of the easiest questions you will do. Contextually, it's a bit difficult. All right, so I'm going to give you a couple minutes, see if you can figure that one out. Whoops. So this is the first type of system question that we have dealt with, okay? And in a system, we have more than one mass. Okay? The arrangement of those masses usually determines how the system moves. But the thing we need to remember about any two connected masses in any system is that they are connected. And as a result, they have to move in the same way. All right? Like if I have, let's say, like over a pulley, for example, a really heavy object on one side and a really light object on the other, which one moves faster? They move at the same speed. One pulls the other. Okay? Even though one is heavier, I mean, all things fall at the same rate, but okay, the big part of this is that the heavier object is going to fall and the lighter object is going to rise over like just that kind of a pulley. But they have to accelerate at the same rate because they're connected. Right? One can't go faster. The falling mass can't fall faster than the one that goes up, or they would break, or whatever connection they have would break. Everyone follow me there? Okay, so all parts of a system accelerate with the same magnitude, not necessarily the same direction. It is possible for them to go different directions, right? One is going down, one is going up, but the magnitude of the acceleration for all parts of a system is the same. Okay, so that's probably something you'll want to make a note of somewhere in your notes here, is that for any system, okay, have the same magnitude of acceleration. And the same is true here, because really, what is this person pulling? 30 kilograms. Okay, yeah, sure, the rope that he's pulling is only directly connected to the 10, but the 10 is connected to the 20. They have to go together. Okay, and they have to go at the same rate because otherwise one would run away from the other or one would catch the other, and that's not going to happen. Okay, at least not while he's pulling. Everyone okay with that? Yes? Okay, so really what we have here is a 30 kilogram system being pulled this way by 55 newtons and resisted this way by 44.1 newtons. That's really all that's going on here. All right, so can I calculate the net force on the system? Yes. All right, so I'm going to go 55 minus 44.1, which should be 10.9, right? All right, so my net force is 10.9 newtons forward or to the right here, okay? Now I can calculate the acceleration, okay? What do I divide by? 30, Okay, now here's how a question like this will trick some people. If I was asking this question, I wouldn't ask for the acceleration of the system. I'd ask, what's the acceleration of the 10 kilogram block? And I would catch a bunch of you because a bunch of you would go and divide by 10. Okay, instead of dividing by 30. Remember, even in this situation here, I'm still pulling all 30 kilograms. Okay, the 10 is part of that. All right, so to get the acceleration then, we've got F net divided by mass. So that's going to be our 10.9 divided by 30. Okay, so we got 0.36 meters per second squared. Okay, and in this case, can I put a direction on that? Yes. Yes, I can. They're both moving in the same direction. If this was that pulley question that we just talked about, where one mass was moving up and one mass was moving down, the question could only ask, what is the magnitude of the acceleration of the system? It could not ask for just acceleration because parts of the system are moving in different directions. Okay, but in this case, I can say forward. Yep. Then you would put a direction. Yeah, if it said like the heavier mass, then you would say down. The lighter mass would be up. Okay, so big thing we need to remember here is that in systems, so anything that has two or more connected masses, the magnitude of the acceleration of those masses will be the same. That is, the net force acts on the entire system. Okay, we can still break the system down into individual parts. Okay, and find, you know, the force of whatever on this part and the force of whatever on that part. We can still do that. But when we get to the net force is on the entire system. Last question. Yeah, did they give right? Sorry, they gave right. Sorry, I shouldn't say forward then, right. Yeah. Okay, so any other questions on the basis of systems? Okay, the basis of systems. Net force acts on the whole system. Acceleration of all parts of the system has the same magnitude. All right, I want you guys to try question number 1 and question number 2. Okay, they both have to do with this system idea. All right, and question number 2 is dealing with the two blocks we had before. Okay. All right, I'll give you a couple minutes on number 1 and then we'll go over number 1. The answers are here, okay, so you can check them as you go. Okay, so number 1, again, is not a mathematically difficult question, but it's contextually difficult. Okay, and that's, again, where the difficulty comes in with Newton's second law stuff. So I've got 2 buckets of nails hung one above the other, and they're pulled up to a roof by a rope. Each bucket has a mass of 5 kilograms. All right, so if I'm drawing a picture of this, okay, I've got some force that I don't know pulling a 5 kilogram bucket that's attached to another 5 kilogram bucket. All right, so I've got something like that. And then I've got, obviously, gravity pulling down. Everybody all right with that? Okay, what do I know about these 2 buckets that would be true? One, same mass. Okay, and same weight because they're both on Earth, but same mass. Okay, and as I start pulling them, they're going to accelerate at the same rate. So it might be possible for me to determine the acceleration of one of them, and it would be true for the other one. So sometimes you want to solve it as a system, and sometimes you want to break it up individually. Okay, so in this one, I want to break this one up because it tells me that the tension in the rope connecting the buckets, that's this force, is 60 newtons. It doesn't tell me what this one is. I mean, I could assume it would be twice that, but I don't know that for sure. Okay, so I know this force is 60 newtons. Can I calculate this force? Yes, I can. Okay, it's the force of gravity, and it's going to be 5 times 9.81, which will be 49.05 newtons. Okay, can I calculate the net force on the bottom bucket? Yes, I can. Okay, as a result, I can find the acceleration of the bottom bucket and know that that's the acceleration of the system. Okay, so sometimes we have to do that. Sometimes we have to look at individual parts and then apply that to the whole system. Other times we have to solve for the system and then apply to individual parts. Okay, so that's what we're looking at here. So I'm going to just use this part and calculate my F net. Okay, my F net will be 60 minus 49.05, so that'll be 10.95 newtons. And then I'll calculate the acceleration by going F net divided by m. What m am I using now? 5 kilograms. I'm only dealing with this bucket right now. All right, so 10.95 over 5 is going to give me what, 2.1? 2.19. Do I have 3 significant figures? I only have 2, so 2.2 then. Right. Yeah, so 2.2. All right, so the acceleration of both buckets is 2.2 meters per second squared up. Okay. Everybody all right with that one? Okay, so question number 2 is going to require you to do something similar. Okay, we already know that the acceleration of this system, okay, we already calculated that. Okay, but now we're being asked to calculate some individual forces within this system. Right, so they're telling us, okay, the force of friction on the 10 kilogram block is 14.7 newtons. Calculate the tension in the rope connecting the 2 blocks. So we're looking for the tension here. Okay, all the information from the first one we did still applies. All right, so that would be the total friction on the system is 44.1. Okay, and the applied force here is still 55. Right, what we're looking for is how much force is there right here. All right, so I'm going to give you guys a few minutes on that. There's actually 2 ways to do it, and they both arrive at the same answer. Right, we'll see how many people do each one. Okay, so we already figured out, remember, the acceleration of this whole system. All right, so I'm just going to delete what I have here. Okay, we figured out in the first part that the acceleration of the system was 0.36 meters per second squared. Right? What does that mean the acceleration of each box is? That can help you find out something about each box. If you break this up now into the 2 boxes, you can find something out about each box using that number. All right, so like I said, there's 2 ways to solve this, each way using a different box. Okay, I can solve this using the 10 kilogram box. I can solve this using the 20 kilogram box. It doesn't really make any difference which one I choose to use. All right, so I'll show you both. I'm going to start out with the 10 kilogram box. Okay, I know that there are 55 newtons worth of force pulling on the 10 kilogram box directly from the hand out front. Everybody with me there? Okay, there are 2 forces resisting the 10 kilogram box. One of them is told to me, the force of friction. What's the other one? The 20 kilogram box. And how is that resistance being transferred to the 10 kilogram box? Through the rope. Is that what they want you to find? It is. Okay, so this is the force I'm being asked to find. It's the tension in the rope between the boxes. So right now, I know the acceleration of this box, and I know its mass. What can I find out about it? I can find the net force acting on just this box. All right, so I'm going to do that first. All right, so F net is going to be 0.36 times 10 kilograms, mass times acceleration. All right, so that's going to give me 3.6 newtons as my net force. That's the net force acting on the 10 kilogram box. What's the other way to calculate net force? What do I do with all the forces? Add them up. The vector sum of all forces is the other way to get this number. So I could say this, that the net force is equal to 55 newtons plus negative 14.7 newtons plus the tension in the rope, the force I don't know. Can I find out the force I don't know now? Yeah, because I know all the other ones. All right, so that's what I'm going to do. Okay, I'm going to bring these other ones over, okay, and I'm going to go 3.6 minus 55 minus negative 14.7 equals T. Okay, that's isolating that missing force. All right, so we're going to have 3.6 minus 55 minus negative 14.7. Okay, so our tension in the rope is 36.7 newtons. Two significant figures, it's 37 newtons backwards. All right, everybody with me on how I did that? Okay, so again, that's what I was telling you before. I can apply stuff from the system to the individual masses, and then I can treat the individual mass like it's an individual. I don't have to worry about the other mass. Okay, that's what I had to do here. Now I can do the same thing with the 20 kilogram mass. Okay, so if I chose to use the 20 kilogram mass, okay, I have a force of friction that is resisting it and the force they want me to find. That's all that's pulling it forwards. Everyone okay with that? All right. Now, I actually have to calculate this force as well, which is why most people don't do it this way. Okay? I have to go 44.1, the total friction, and subtract how much of that was only acting on the 10 kilogram block in order to get what was left acting on the 20 kilogram block. Okay, so I've got my 44.1 minus 14.7. Okay, whoop. Okay, so we got 29.4 newtons here. Okay. And I'm looking for T. What can I find out about this box since I know it's accelerating at 0.36 meters per second? It's net force. All right, so F net for this one, okay, is going to be 20 times 0.36, which will be 7.2 newtons. All right, so now I've got the net force there, and now I'm going to do the same thing I did before. F net is equal to the force of friction plus the tension. So I'm just going to subtract the friction. So I got F net minus the force of friction equals that pulling force that's forward. So that'll be 7.2 minus negative 29.7. Okay, and that's going to give me, again, 37 newtons. Okay, so it didn't matter which box I used, I get the same tension. Right. Again, nothing mathematically difficult there, okay? But contextually, it's challenging, okay? We haven't seen something like that before. We have to start seeing the forces within a system and how they work. Okay. All right, anybody need that one anymore? That's about as tricky contextually as they get, okay? Just so you know. All right, so here's another system question. I've got these two masses hung over a pulley. One's 35, one's 25, okay? I want you to determine, actually I'm gonna change this. I'm gonna say, okay, I want you to calculate the acceleration of the 25 kilogram mass. All right, still a system, don't forget that. So what are the forces acting on this? Gravity. The gravity is pulling on each one of the masses, agreed? Okay, so I can calculate the force of gravity on each mass pretty quickly, okay? So the force of gravity on the 35 kilogram mass, all right, so 35 times 9.81, all right, it's going to give me 343.35 newtons. And then for this one here, it's going to be 245.25, right? Yeah. Newtons. All right, so those are the two forces acting in this system. Now I'm going to draw the free body diagram without the pulley. Those are the forces acting on the system, right? I've got more gravity going one way than I've got going the other way. So here's what I end up with then. Okay, I'm going to end up with my net force being the vector sum of all forces, 343.35 minus 245.25, which should give me 98.1 newtons. Agreed? All right, so my net force on the system is 98.1 newtons. The acceleration then of the system is F net over m. What m do I use here? 60. Okay, both of these masses accelerate at the same magnitude. One's up, one's down, right? So I still find the acceleration of the system here, 98.1 over 60, okay? And that will give me the acceleration of the system, okay? 1.6 meters per second squared, and then all I do is add what to that at the end? Up, because I asked about the 25 kilogram mass, okay? This is the acceleration of the system, okay? 1.6, and then I add just the up because I was asked about a specific part of it. Right? So again, the reminder here is that all parts of the system accelerate at the same rate. I can't put a direction on that number because it's for the system. If I want it for the 25, then I can say up. So pulleys always work that way. What you want to do is calculate the forces involved and then straighten and eliminate the pulley. Okay? Yes, gravity was pulling down in both cases, but because there was a pulley in the middle, the two gravitational forces were opposing each other, which is why I drew them horizontally in opposition. Okay, everyone all right with that? Okay, because I know it looks weird when I draw gravity going left and right, okay? But essentially over the pulley it was in opposite directions. That force is pulling down on the 25. You're right. But okay, the 25 still moves up because that force is less than this force, right? The net force is still.
Just weird. I just don't get the sideways.
Well, that's what I'm saying. It's like I draw it sideways because these forces are, even though they're both down, are pulling against each other because there's a pivot point, right? It's no different than if you're lifting something using a pulley, right? You pull on one side, you're pulling down, but the object's moving up, even though there's a force pulling down on it on the other side as well. Yeah. Okay, similar thing. Okay, similar thing. System here. Okay, give this one a try. Now, there's the driving forces are the two pails. Okay, we've got this tire on a table. I don't know who sets these kinds of things up, but that's what we have. Okay, and so we're just looking to see which way, okay, is it going to go. Now they are asking for the acceleration of the system, okay, not of any one individual part. Doesn't mean the individual parts aren't important. The forces on the individual parts are important, okay, but I want the acceleration of the system in general. So I'll give you a couple minutes on that. So for this question, we want to do a similar thing to the last pulley, okay, and that is we want to kind of eliminate the pulley, right? So we know we have an 8 kilogram pail, a 6 kilogram pail. So pail B is our 8 kilograms, so it's the heavier of the two. Okay, pail C is the other one, and then our tire is 20 kilograms. So we've got in total here how much mass? 34 kilograms. All right, so I'm going to draw this and say, all right, I've got 34 kilograms worth of mass in the system. Okay, that system is being pulled this way by a force of gravity and this way by a larger force of gravity. All I have to do is calculate the two of them. All right, so I'm going to take my 8 times 9.81. All right, so we got 78.48 newtons going this way, and 6 times 9.81 going the other way. All right, so 58.86 newtons going that way. Those are the forces acting on the system, and since they want the acceleration of the system, that's all I have to worry about. I don't need to worry about any individual parts beyond calculating those two forces of gravity. Right? Now, what can I calculate with those numbers? Right, the net force. All right, so F net is going to be 78.48 minus 58.86, which is going to be 19.62 newtons. Hey, everyone all right with that? All right, so now I've got my net force. Now I can calculate the acceleration of the system. F net over m, so 19.62 divided by 34 kilograms. All right, so we're looking at 0.58 meters per second squared. Okay, and I can't put a direction on that. That's the acceleration of the system. It's a magnitude only because different parts of the system are accelerating in different directions at that rate. Okay, if the question had asked about the truck tire, then I would say left along the table. Okay, if it had asked about pail C, I would have said up. Okay, pail B, down. Okay, everyone all right with that? Same number, but different directions if they asked for individual parts. All right, I'm going to give you a 3 or 4 minute break here, okay, and then we'll look at something else.